So we'll go ahead and get started. So it's my pleasure to introduce today's seminar speaker, Professor Renu Malhotra. So Renu got her PhD from Cornell University, and after that went on to a postdoc at Caltech, and then a position at the Lunar and Planetary Institute before ending up at University of Arizona. So Renu has been awarded numerous prizes for her work in planetary dynamics, including being an elected member of the National Academy of Sciences and the American Academy of Arts and Sciences. She's currently the Louise Foucault Marshall Science Research Professor and Regents Professor at University of Arizona, and she's an expert in exoplanets, the Kuiper Belt, asteroid belt, orbital resonances in the solar system, meteor bombardment history of the solar system, and she is famous for pointing out that the Neptune and Pluto resonance provides evidence for orbital migration of the giant planets during the solar system's early history that's revolutionized our understanding of how the solar system formed. And I think we're going to hear some more about Pluto today. So without further ado, I'll let her take it away.
Thank you, Sam. Thanks, everybody, for trip. Well, here in a while, but I got back to Pluto recently, and I'm going to tell you a little bit more that we've learned. So here, very brief history or background that Pluto's orbit is weakly chaotic, but it's stable on gigayear timescales. And Pluto is very interesting for its role in revealing the orbital migration history of the giant planets through its orbital resonance with Neptune. And one of the mysteries of Pluto that's been still a puzzle is its inclination. Its orbit is significantly tilted to the plane of the planets, and the reason for this is only partially understood. Now I'll explain what I mean by partial understanding. And this is what's motivated me to come back to the problem of Pluto recently. And I'll tell you off the bat that I actually didn't make any progress on understanding Pluto's inclination. But instead, we did get some new results on the role of Jupiter, Saturn, and Uranus on Pluto's long-term orbital stability. And the main takeaway, I'll tell you right at the beginning, is from this talk, if you hear nothing else, take away nothing else but this. What we learned is that there's a fortuitous orbital arrangement of the inner giant planets, Jupiter, Saturn, and Uranus, so other than Neptune, the outermost one, which defines a relatively narrow zone of stability for Pluto-like orbits. And this zone is bounded by strong chaos. So in this zone, the orbits are stable for gigayear timescales, whereas near the boundaries, the instability timescales range from millions of years to hundreds of millions of years, so much shorter than the age of the solar system. So that's a little novel understanding, but I should also say that it's very hard to do anything new in the solar system. So there's lots of people who've thought about these problems, and what we've added recently is only an epsilon amount to that. This was work, the new part was work that was published in PNAS earlier this year. And that's the citation. So just to give you the background, since many of you probably don't think about the solar system every day, this is the scale of the solar system here. Contrast with most of the solar system, Pluto's orbit is this rather eccentric and inclined orbit. So back in the 1990s, there were 9 planets in the solar system. Pluto was the 9th one. And Pluto did not fit in with the rest of the solar system. And I guess from a 10,000 foot view of the solar system, here we are out there, close in at 1 astronomical unit. Pluto is out beyond Neptune. Its perihelion is just inside of Neptune, and its aphelion goes roughly twice as far as Neptune. It more or less spans what's known as the Kuiper Belt. So the Kuiper Belt has an inner edge close to Neptune, just outside Neptune's orbit, goes out to about 50 astronomical units, and the whole solar system is surrounded by the Oort cloud. So all these small bodies, the non-planets, are very interesting for understanding the dynamical history of the solar system, because we can find clues that are imprinted in their orbital distribution, in their chemical properties, their physical properties, for deciphering the history of the solar system. And Pluto is one of those objects. So Pluto's orbit is eccentric. Pluto is eccentric, and I guess I'm saying that a little tongue-in-cheek. Its orbital path overlaps that of Neptune. We see that here. This is a top-down view. Neptune's orbit is pretty circular. Pluto's orbit is quite eccentric. It has an eccentricity of about 25%. It's also tilted to the plane of Neptune's orbit and the other planets, which are more or less in that same plane. Pluto's orbit is tilted by about 17 degrees. So this is a side view of Pluto's orbit. And we'll see some peculiarities of this. So even though its orbit overlaps that of Neptune, it's not in any danger of colliding with Neptune. And we can see that by going into a frame that's co-rotating with Neptune. So Neptune is doing this little jiggle here. It's we are in a frame that's rotating with Neptune's orbital velocity, orbital angular velocity around the sun. So in that frame, Pluto does this retrograde trace. And you can see that at perihelion, when its distance is closer to the sun than Neptune's, it avoids the location of Neptune. Okay, so its perihelion oscillates alternately for plus 90 degrees from Neptune and minus 90 degrees from Neptune. And these are what I'll be referring to later as azimuthal libration. So relative to Neptune, the azimuth of Pluto's perihelion oscillates like so. And this is because, and so this is an oscillation rather than a continuous drift, because there is this orbital resonance between Pluto and Neptune. The period of Pluto, orbital period, is 1.5 times Neptune's orbital period, and Neptune's little gravity shepherds this kind of oscillatory motion. Going back some 3 decades, more than 3 decades ago, Jerry Sussman and Jack Wisdom published this paper in the early days when computers were becoming powerful enough to be able to do orbit propagations for timescales comparable to the age of the solar system. They did a orbit integration of the planets for 845 million years, and reported what they call numerical evidence that the motion of Pluto is chaotic. What they did was they took tiny nearby Plutos and asked how they diverge over time. And they found that there's an exponential divergence of nearby initial conditions with an e-folding time quite dramatically, very short, only 20 million years. And so these are some figures showing this exponential divergence. And this was the first detection of chaos in the solar system, dynamical chaos in the solar system. Shortly after, there was a competing group in Italy that had been also trying to do these very long-term simulations, numerical integrations of the solar system. This was a group led by Andrea Milani, and they had done also a very long integration, which was, I think, about 100 million years. And they reported that Pluto was engaged in a number of orbital resonances, not only this resonance with Neptune, but they found through a Fourier analysis of Pluto's orbital parameters, orbital elements, that there were a number of resonances that they could identify, things that they call super resonances that had long periods, like this one had a period of 34 million years. And I think it was eventually kind of tied to this, this chaos that was detected by the longer integration. But these guys also disputed the evidence, this numerical evidence that Pluto is chaotic. And they came up with an idea, a concept that there's stable chaos. And the reason was that they found no gross changes in Pluto's orbit. So there's a positive Lyapunov exponent, but over these hundreds of millions of years, the shape and orientation of Pluto's orbit barely changes. Okay, so there's chaos somewhere hidden, possibly in the phases, doesn't show up in the shape and orientation of Pluto's orbit. And so these guys called it an example of stable chaos. So over more than 50 Lyapunov times, there's no significant change in the overall properties. And so they came up with this concept called stable chaos. And it's still out there in the literature, not super well understood. Fast forward another decade or so, and we moved on to even faster computers, more powerful computers that could now explore not only individual, single orbits or a single state of the solar system propagated forward, but many solar systems. So you could do a whole exploration of the phase space. And this Japanese group, Takashi Ito, is actually my collaborator on this recent paper. Takashi was doing this for his dissertation. So he did many long integrations going plus 5 gigayears in the future of the solar system and also going in the past. And this is a projection in real coordinates, so XY, top down in the solar system. And here's 3D of the orbits of the outer planets, including Pluto. And over this time span, they found, again, like that Italian group, that nothing much happens to Pluto, even though they could also recognize that there's a positive Lyapunov exponent. So Pluto can be interpreted as being weakly chaotic, but stable on gigayear timescales. And more specifically, that Pluto's orbit is actually robust against small changes to its orbital parameters. So what we set out recently to ask was, what about the role of changes to the planet's parameters? How robust is Pluto to the orbital parameters of the planets? Now, Pluto, I mentioned to you that Pluto has this role in our understanding in revealing the orbital migration history of the giant planets. And that is to say, the planets have migrated. So we've understood this for some time now. This was an idea I published some time ago, that Pluto, we can understand some of Pluto's peculiarities if we allow that Neptune didn't form where we see it today. Today, it's 30 astronomical units from the sun. And Pluto is in this 3-to-2 resonance with Neptune. But if Pluto formed in a normal coplanar, more or less circular orbit, closer, when Neptune was closer to the sun, as Neptune migrated outward, then it would have grabbed Pluto in this resonance, and Pluto would have migrated along once it got captured in this resonance. And that's where we would, once the migration stopped, the solar system reached its more or less its current state, Pluto would be in this resonance. And there's an adiabatic invariant that connects the same major axis of Pluto and its eccentricity. And because of this resonance, we can then back out how far Neptune had migrated. And so Pluto's eccentricity tells us that Neptune must have migrated by at least 5 astronomical units, so that during this migration, its eccentricity would have been pumped up to its present value from a nearly 0 value prior to that. This produces this idea, this simple model, predicts a pileup of resonance of objects in resonances, in Neptune's resonances. There's not only the 3-to-2, but other resonances of Neptune. And this is a theoretical prediction from a very simple model, numerical model of the migration. Now, today, we have more than 4,000 Kuiper Belt objects that have been discovered. Many of them are in these orbital, they're piled up in these orbital resonances in eccentric orbits. Okay, so by looking at the eccentricities of these resonant objects, we can actually figure out something. Oh, there's Pluto. So Pluto is one of these common, so it's no longer unique. It's one of dozens of, actually hundreds of objects that are captured in this 3-to-2 resonance. And they're called Plutinos because they share Pluto's orbit. That's an informal name. I don't think the IAU has officially called them Plutinos. And by looking at these distributions of the eccentricities, also inclinations, we can estimate that Neptune must have migrated out by more than 10 astronomical units. And it's a lower limit because it's a leaky bucket here. When eccentricities get pumped up too large, the resonance is no longer stable. And so any Plutinos, for example, that had been captured much before Pluto was, would have had their eccentricities excited even more. but that's an unstable region. So the Plutinos leave once their eccentricities are above about this maximum value, which is just short of about 0.4 eccentricity. So that gives us a lower limit on how much Neptune has migrated out. 10 astronomical units means that Neptune started out roughly where Uranus is today, okay? So, or closer in. How did this migration happen? It's thought to have been fueled by leftover planetesimals. So in the early days of the solar system, as the planets formed, there was a lot of debris. So the solar system had a debris disk, lots of small bodies. And the planets, the larger bodies, were scattering them gravitationally. And the scattering had a back reaction on the planets. So the solar system was cleared out. Today, it looks pretty clear, except for the asteroid belt and the Kuiper Belt, where there are surviving planetesimals. But everything else was thrown out mostly of the solar system. And these ejected objects carried away energy and some angular momentum. And the back reaction was that the planets, they started out closer together and spread out. And because Jupiter was doing most of the heavy lifting of ejecting planetesimals, Jupiter's orbit must shrink. It's the source of energy. And so Jupiter's orbit shrinks, the other planets are lighter and their orbits move out. They actually transmit angular momentum and energy to Jupiter. And then at the end, what's left is a cleared zone amongst the planets, and only the stable regions beyond Neptune are still populated. So this is the surviving debris. This is the same process, we think, that formed the Oort cloud that exists surrounding the solar system. So there's other observational evidence of this migration. The asteroid belt has missing asteroids. So if you look at the asteroid belt and ask if the planets remained in the configuration we find them today, what kind of structure would we expect in the asteroid belt? Where would we expect asteroids and where would we expect gaps and so forth? And it turns out that the present configuration is not consistent with what we actually observe in the asteroid belt. And however, if we allow the planets to migrate from the way we understand from the Kuiper Belt, the asteroid, some of the structure in the asteroid belt becomes very consistent with what we actually observe. Okay, so this is like an independent evidence. Kuiper Belt is consistent then with what we learned about the structure of asteroids in the asteroid belt. There are many details about this, and I'm just giving you a big picture here. It's also, this migration is also linked to, possibly linked to the late heavy bombardment. This was something we learned from the Apollo program, when the Apollo astronauts brought back samples from the moon, and those samples were studied in laboratories. One of the major scientific conclusions from those samples was that the moon had been bombarded, had a spike of meteoritic bombardment late in its history. So the moon formed about 4.4 gigayears ago. The crust of the moon is about 4.4 gigayears old. And it solidified then, but then it was bombarded, and its thermal history was reset about 500 million years later at about 3.9 gigayears. That's known as the late heavy bombardment. It's late, meaning of course, it's early in the solar system, but it's late relative to when the planets formed, when the moon formed. And so this has been linked to the migration of the planets, that as the planets migrated, there was a lot of bombardment of the planets going on, but that clearing process stopped. The source of the bombardment terminated around the time that the planets reached their current configuration. And then this evidence is also linked to two different crater size distributions we find on the planet. So there are older craters and younger craters. And these are also, there's a nice story that links the late heavy bombardment versus what comes later, the current bombardment rate that's going on, that we have meteoritic bombardment on Earth even now and on the moon. So those are two different crater size populations, and there's a neat story that connects the old and the younger craters. So back to Pluto, more recently we've had a visit with a spacecraft the New Horizons spacecraft that flew by Pluto in 2015. It was launched about 10 years before that. And Pluto has turned out to be even more intriguing. It's a bona fide little miniature solar system with five moons. And it's not just a point of light in the sky. It's a bona fide geologically active world. Okay, so we have close-ups of Pluto and its big moon Charon. So Pluto is quite geologically very interesting. Turns out to be like a little planet. Okay, but I'm going to talk about its orbital dynamics, back to Pluto's inclination. So there are many puzzles about Pluto. And so what I'm going to touch on today is this problem of Pluto's inclination. Okay, so it's unusual. And if you take a very simple model, a simple simulation of this planet migration and resonance sweeping, and ask what happens, what kind of Kuiper Belt structure do we expect? What kind of inclinations and eccentricities do we expect for these resonant objects? I should say this is semi-major axis on the horizontal axis, inclination in this lower panel, and eccentricity in the upper panel. And we're going from where Neptune is at 30 astronomical units out to about 60 or 70 astronomical units here. So this is a simulation where test particles are started out beyond Neptune. So Neptune starts out closer to the sun than where it is now. And these test particles are these little gray dots that you can see down there. They start in zero inclination or nearly coplanar orbits with the planets, and in nearly circular orbits. And at the end of 5 gigayears, as the planets migrate, there's a simple model of migrating the planets. This is not a full n-body simulation of migration. It's a quasi, it's like a restricted n-body. So we have the planets, and we have massless test particles, and we ask what kind of distribution do they end up in at the after 5 gigayears. And what we see is this is the 3-to-2 resonance with Pluto. It gets populated. The 2-to-1 gets populated. Other resonances get populated. And you can see how the eccentricities and inclinations get excited. So Pluto is a typical one in terms of its eccentricity, but not so typical in its inclination. So these kinds of models find it very hard to account for inclinations greater than about 10 to 12 degrees. So Pluto is an outlier in its inclination. And actually the real population of Plutinos goes up even higher. There are Plutinos that are out at 40-degree inclinations. Although they're rare, they're not dominant. Most of the population is lower down. But this range is difficult to get through planetary perturbations. So more sophisticated models also don't have a satisfactory solution for the inclination excitation in the Kuiper Belt. So let's take a closer look at Pluto's inclination, or rather Pluto's orbital dynamics. So I've shown you this azimuthal oscillation already. Pluto has this other peculiar thing, which I call the latitudinal vibration. And so this is a projection of Pluto's path in about, I think, over about 40,000 years. This oscillation has a 20,000 year period. If you look sideways, okay, so here this is a projection in the z-axis and the y-axis. And you can see that here in this animation. When Pluto comes to perihelion, it's above the plane of the solar system. Okay, so its latitude at perihelion is always up here at a high latitude. And over even longer times, if you propagate its orbit over very long times, this latitude of where it reaches perihelion just bobs up and down a little bit. Okay, it doesn't go all the way into the plane of the solar system. And that's really peculiar because generally orbital planes precess all the way around. And if Pluto were doing the normal precession that most planets' orbits do, its perihelion would go all the way into and below. And so this oscillation, this libration of its perihelion is another constraint. It is another resonance that Pluto is engaged in. And I'll show, and so these two resonances are characterized by two critical angles. This is called the mean motion resonance angle. This is a combination of three times and 2 times the mean longitude, so Pluto and Neptune, and Pluto's longitude of perihelion. So this is known as the 3:2 critical resonant angle, and it oscillates around a mean value of 180 degrees, plus minus some amplitude. The other resonance, this latitudinal resonance, is characterized by this angle, the argument of perihelion. This is the angle that we measure from Pluto's orbit nodal longitude of ascending node on, say, Neptune's orbit or on the invariable plane of the solar system. We measure it along Pluto's orbital path from the nodal line to its perihelion. And this angle oscillates, and I'm going to show this to you in this Cartesian projection, where the amplitude is the eccentricity and the polar angle is the argument of perihelion. Whereas this one I'm going to show you as a time series with the behavior, this oscillatory, the libration of the critical resonance angle. And so some time ago, Leveson and Hal Leveson and Alan Stern did this numerical exploration of the neighborhood of Pluto's orbit in terms of the latitudinal amplitude of libration and the azimuthal amplitude of libration. And Pluto lies, so all these black dots are regions where we have stable orbits, and the open dots are, this was a limited set of initial conditions that they could do. They found that Pluto's location, at least in this projection, in terms of the amplitude of azimuthal libration and latitudinal libration, Pluto lies close to the edge. It's kind of a, you can see that it's sort of a fractal structure. There's not a continuum, but there's a rough line of stable versus unstable locations. So high amplitudes are generally unstable on both sides, both high amplitudes on the critical resonant angle and this argument of pericenter, whereas smaller amplitudes are more stable. And Pluto lies somewhere near the boundary. Okay, so it's far. Sorry, could you say? Oh, these are, I think in one case they tuned one parameter, and in the other case they tuned a different parameter. So it's two different simulations, but exploring the same parameter space. They had other parameters that were tuned differently in the two simulations. Okay. So think of it as two samples of a bigger parameter space. So the takeaway from here is that Pluto's orbit is robust to small, but not to moderate changes to its orbital parameters. If you move its libration amplitude in that resonant angle by quite a bit, then it becomes unstable. If you move its libration amplitude in this direction of the latitudinal librations in that direction, it becomes unstable. But it's close to, but not super close to that instability and that boundary. Yeah. In this case, you get very strong chaos. The orbit doesn't stay in the resonance. It leaves the resonance. It can be ejected. Collisions are, of course, very low probability, but ejections are more likely.
It's just living on the boundary.
It's living close, but not super close. I'll show you how far it is. So here's the boundary. So the boundary for Pluto's exact inclination and eccentricity is about here in this resonant angle. Its amplitude is actually significantly away from that boundary. There is this other boundary that I've drawn for different inclinations and eccentricities. Stability can be narrower, okay? But for Pluto, where it is, its range of stability is broader than where it actually is. Okay? And then in terms of the argument of pericenter, this is what Pluto is doing. This is the range of stable librations. For similar eccentricities and inclinations, the libration amplitude range can be narrower. Okay, and so the timescales I'd like you to remember are, so this is a short period, relatively short period, 20,000 year oscillation period. This is a 4 million year oscillation period. So this is a weaker resonance in a sense, because it has a much longer oscillation period. So the restoring forces that are maintaining this resonance are weaker. Okay, they're not as strong as the forces, the gravitational forces that are maintaining this this resonance, this oscillation. So this is weaker, which means it's also more vulnerable to other perturbations. But numerical experiments tell us that for Pluto, with nearby orbits, orbits that are close to Pluto's orbital parameters, both of these librations persist steadily on giga-year timescales. But if you go moderately away from Pluto's neighborhood, then these orbits may or may not be stable. Okay, what did I want to say here? So yeah, so there's a well-understood theory for the azimuthal librations, this mean motion resonance. We also understand how it's related to its eccentricity, but the latitudinal vibrations are not nearly as well understood. Okay, they're thought to be related to a phenomenon known as the VZLK phenomenon. Some of you may have heard of this as the Kozai resonance or the lead-off Kozai effect. I'm calling it the VZLK effect because one Zaipo, actually my co-author Takashi Ito, did an in-depth historical study and discovered that Hugo one Zaipo more than a century ago had already discovered this effect. It's an effect in the three-body problem, and I'll show you what it is now. Let's see, how am I doing with time? 3:30. Okay, we started at 3. Okay, so I'm okay. So one Zaipo was a Swedish astronomer, lived more than 100 years ago. Lidov was a Russian mathematician astronomer, and Kozai was a Japanese astronomer. And back in 1962, they independently discovered this effect. And apparently, they may or may not have known about one Zaipo's prior discovery. This effect became, everybody, a lot of it had a resurgence of interest recently because after the discovery of exoplanets. And also it has a role in understanding stellar binaries and stellar multiples and the eccentricity distributions in stellar systems. So what is this effect? It's a three-body effect. If you have a star and a small object orbiting the star and a distant perturber, here's a distant perturber, then if the small body's orbit is not coplanar with the distant observer, with the distant perturber. So let's say we start off the small body in an inclined orbit, in a circular orbit, but that's inclined to the perturber's orbit. Then above a certain inclination, a relative inclination, the circular orbit is unstable. It becomes stretched out and becomes an elliptical orbit, and you can see that. And as it becomes stretched out, it also goes closer to the plane of the distant perturber, and it does this oscillation. So the inclination and the eccentricity trade off with each other. So the circular orbit becomes eccentric, and the inclination goes down, and then back and forth. Okay, so so this is an instability of circular orbits. There are other aspects to this. There's also this oscillation that's possible. Okay, that's this trade-off between eccentricity and inclination. And so that is this latitudinal vibration that I was describing. So this VZLK effect supports these librations of the argument of pericenter or the latitude of perihelion, and makes these coupled oscillations of eccentricity and inclination. This is a cartoon from, I think, the Russian press. When Lidov discovered this, he realized that if the moon had been in a polar orbit around the Earth, it would have long ago crashed into the Earth because of this three-body effect. Okay, the moon's orbit is nearly coplanar with the Earth's equator. It's a little bit off, but had it had a very large inclination, bigger than that critical inclination turns out to be around 40 degrees, 39 degrees, solar perturbations. So that's our third body, the distant perturber. The moon would have crashed onto the Earth. Actually, that's not quite true because it turns out the Earth spins fast enough. It has sufficient second harmonic of its gravity that it actually kills this quasi instability, this VZLK instability in the case of orbits around the Earth. That's why artificial satellites are able to be on polar orbits for long periods of time, okay? Although they do need some station keeping. Right, so there's this critical inclination above which this VZLK phenomenon kicks in. And when the perturber is a distant perturber, that's the one that Von Zypo, actually, Lidov and Kozai looked at. The critical inclination is about 40 degrees when the object is very close or very far from the perturber's orbit. But as the orbit gets bigger and bigger for the inner test particle or perturbee, as the perturbee's orbit gets closer to that of the perturber, this critical inclination goes down. Okay. Now, for the outer problem, where the perturber is interior, it turns out to be rather different. The dynamics and the critical inclinations are actually always large. They are when the ratio of the semi-major axes is small. So your perturbee is far away from the perturber. Perturber is inside now. The inclination is the critical inclination is around 60 some degrees. Okay, and even when you get close, the critical inclination doesn't go down a whole lot. You can see the scale here is 54 to 64 degrees. Okay, so you need a very large inclination when your perturber is inside to do this VZLK phenomenon. So how do we apply this to Pluto? How is this relevant to Pluto? So apparently Pluto is doing this VZLK without having this large inclination. This is Pluto's ratio with its perturber, the interior perturber, which is Neptune. And the critical inclination in that problem is around 57 degrees. Okay, so Pluto-like orbits should be doing this VZLK oscillation if they had inclinations of 57 degrees or higher. But Pluto's inclination is only 17 degrees, and it's still doing this perihelion latitude oscillations. How is that possible? How is it able to do that? So Neptune's perturbation, it turns out that Neptune's perturbations alone, in other words, the three-body problem here, is insufficient. Okay, so there's more going on to support these oscillations, these latitudinal oscillations. So in this recent work, what we did was something very simple and almost stupid. That we did these numerical experiments. We took subsets. We added to the three-body problem, the three-body problem of the Sun, Neptune, Pluto. We added Jupiter and Saturn and Uranus and subsets of their combinations to see how that affects Pluto's latitudinal perihelion libration. And I'm going to show you pictures like these where I have the resonant angle. And if you see a figure like this time series of the resonance angle, it's doing this libration with constant amplitude. That's a stable solution. Pluto is stable in that model. And so this is actually the full model with all the 4 giant planets here. So Jupiter, Saturn, Uranus, Neptune, and Pluto. And then the second panel I'll show you is this polar plot of eccentricity cosine omega, eccentricity sine omega. This is the latitudinal perihelion libration. So if you see a little arc like this, the orbit is stable. If the solutions you see deviate greatly from this kind of pattern, you'll see that the orbits are unstable and they're strongly chaotic. Oops. Okay, here we go. So this is the highest fidelity model. These are all the subsets of combinations with Neptune, the three-body problem, Neptune, Pluto, Sun, and where other planets have been added. So let me first highlight this one. If this is just the Neptune-Pluto problem, and we don't get that nice latitudinal oscillation of Pluto's perihelion. The perihelion circulates, it goes all the way around, does not do this oscillation. If we add Uranus, just the next, what you might imagine is the next most important perturber because it's the closest. You add Uranus, Pluto's orbit becomes unstable. It becomes wildly chaotic and actually on a time scale less than a few 100 million years. So it doesn't last at all, and so on. So if you go through all of this, you can stare at those figures. What we figured the pattern was the following, that Uranus introduces destabilizing perturbation. Jupiter is more or less stabilizing for these oscillations, these latitudinal librations of Pluto. But no subset of Jupiter, Saturn, and Uranus is sufficient to actually get Pluto's stable latitudinal librations over giga-year timescales. So all three of these planets, in addition to Neptune's perturbations, are necessary to have Pluto do what it's doing. So how do we understand this? So from the point of view of Pluto, what's the role of Jupiter, Saturn, and Uranus? From the point of view of Pluto, Jupiter is zipping around with a 10-year period. Pluto's orbital period is 250 years around the sun. Jupiter is zipping around with a 12-year period. Saturn and Uranus also are zipping around much faster. And so as a first approximation, we can collapse all of the effects, all of the parameters of these planets as rings. We can approximate the effects of these three planets as rings. And actually to the lowest approximation, we approximate them as circular rings. And their effects then is like putting a belt on the sun, okay, having an oblate sun. So you have these rings around the sun, close in, affecting Pluto, which is far away. So if you approximate Jupiter, Saturn, and Uranus as rings, they have an effective gravitational term, J2, an oblateness term. We add it to the three-body problem, and we asked the following question. We said, is there some range of this value of J2 for the sun that will support Pluto's steady latitudinal librations? And we did these simple simulations with a three-body problem, the three-body model of Neptune, Pluto, and the sun, with an oblate sun, with this J2 in this range 0 to 10,000. It's because the J2, the effective J2 is a ratio that goes like this, and the gravitational potential goes like J2 times the radius of the sun divided by the semi-major axis of Pluto. So even though that J2 seems to have large values, its effect is actually small, because it's killed by the ratio of the semi-major axis of the radius of the sun to Pluto's semi-major axis. So is there some range of values of J2 that support Pluto's steady latitudinal librations? And it turns out there is, and it's a narrow range. So this is a log scale. And then right here in the green part is where the latitudinal librations occur. And this is this range. It's around 1500 or 1300 to about 1600. And this blue line is the value for the solar system. So the Jupiter, Saturn, Uranus have an effective value of J2 that lies right here with this blue line. Okay, and so this is the range. So out here, omega rotates. Out here, it rotates in the opposite sense. So actually here, I think it's going retrograde and or the other way around. This one is going retrograde. This one is going prograde. This region, it allows librations, and this region, it's chaotic. This orange region is chaotic. The red region is a fuzzy boundary. Okay, so we can see that a little more clearly here over this expanded range. So there's a narrow range of J2 for an oblate sun that supports these kinds of oscillations, the perihelion latitudinal librations of Pluto. The green one, the green range is stable. The red one is stable, but it's not doing oscillations. Yeah. You could be there, you could be stable. Yes, that's true.
That's very hard to get to that range.
That is, well, actually, it's all of, I can show you so Jupiter contributes this much, about a third. The other planets, actually all of the planets contribute equally, almost equally. Because it's not just the mass, it's also the square of the. It's hard to be very small and it's hard to be very large. Yes, yes. Okay, so we have these strongly chaotic orbits bounding this narrow range where we have stable latitudinal oscillations. And so what does that imply? What that means is that this value, this mass and orbit radius combination of Jupiter, Saturn, and Uranus is kind of fortuitous. Okay? We get a J2, an effective oblateness of the sun, that's just in this range to allow Pluto-like orbits to have these latitudinal librations and be stable. Okay? To have those librations and be stable, both conditions.
Fair to say, for Pluto's exact orbit. You have
For-
excluded that there's other parts of the resonance.
That's
that
true.
wouldn't stay all.
Yes, for Pluto's neighborhood, yes, right.
Use Pluto's vibration and
With Pluto's libration amplitude, with Pluto's eccentricity, with Pluto's inclination. So in its small neighborhood, this is what allows Pluto to survive. Yeah. Okay, so what does that translate into? So if we take this, how close the solar system is to this boundary, that gives us this wiggle room that you can fiddle. So this is the delta J2 for getting to the boundary of the chaotic region. This is relative to a J2 value, which is around 1500. So that's a fractional amount of about 5%. But for each planet, you could then change, if you change the mass ratios of the planet or the masses of the planets by about 20%, you have to maintain the mass ratios. You have you can't change the masses of these planets by more than about 20%, or their semi-major axes by more than about 10% before you get out of this region. Okay, then you'd hit this region here. A little more wiggle room in the other direction. Okay, so there's this is how now if the planets have migrated, how would their effective J2 have changed? And so as best as we understand, roughly speaking, the planets have migrated, as we understand from the Kuiper Belt. All of Jupiter, Saturn, and Uranus would have started out closer together. And I did a very rough calculation of what the effective J2, how much it would have changed, and it wouldn't have changed a whole lot, actually, but surprisingly, because we have if you crush Jupiter, Saturn, Uranus, and Neptune really close together within a few astronomical units of each other, their effective J2 is not too far from where we find it today. It has some range, and over this range, the effective J2 would have started out smaller and increased to its present value as the planets spread out. And from that, what we can learn, we can say a little something that in particular, if Uranus had migrated, so it turns out it's mostly sensitive to Uranus. If Uranus had, because Uranus has the largest migration possibility after Neptune, if Uranus had migrated out by more than 5 astronomical units, then the initial state would have been unstable, and it was transitioned into a stable VZLK of Pluto-like orbits. See? Haven't quite wrapped my mind around exactly what we can say about the constraints on the history of the planet's orbits in detail, but that's one thing we can learn. So let me summarize. In trying to understand better the problem of Pluto's inclination, we stumbled upon this insight that Jupiter, Saturn, and Uranus have this apparently fortuitous orbital arrangement that defines a narrow zone of long-term stability for Pluto-like orbits. And it is bounded by strong chaos. Those pictures you saw have instability timescales of not more than, in that boundary region, the instabilities kick in on timescales of anywhere from millions of years to a few 100 million years. So the problem of Pluto's inclination still needs more work. Okay, I think that was it. Yeah, thank you.
We have plenty of time for questions. So are there any questions in the room? Yes.
Is Triton just is Triton too small to just really have any effects on Pluto? Because I know, also I'm not super knowledgeable about the solar system, but just from my basic knowledge, I know that a lot of people are still kind of confused on Triton and how that sort of system around Neptune was formed. So is it possible that that could have any effect on Pluto?
So Triton is a more or less Pluto-sized object that's a moon of Neptune's. And it's generally, I think the idea is that it was captured in orbit around Neptune during that same process of the settling down of the solar system from an early chaotic state when small bodies are being scattered around. Does it have an effect on Pluto? Well, not directly, obviously, it's not connected to Pluto currently, but something like a Triton-like object probably is the source. A collision with an object like that is the source of the Pluto moon system. It's thought that the giant, the large moon Charon and the retinue of satellites are a result of some kind of impact with a comparable to Pluto, comparable to Triton-sized object.
The Triton can be a Pluto that went unstable.
Triton could be a Pluto that went unstable. Yes, I guess there's that small probability of capturing by Neptune. I'm sorry, yes, by Neptune. Triton is orbiting Neptune.
Thanks for your talk. I just want to clarify. So you mentioned that you need an inclination of 60 degrees to induce ZOK, but Pluto is only 25 degrees, so there's no ZOK oscillation in this case.
Pluto is actually 17 degrees. Yeah.
17, right?
Uh-huh.
So is the inclination, as you're saying, the inclination is mostly driven by the precession of this like oblate sun model, is that right?
Okay, we see from the numerical simulations that the oblate sun will produce these latitudinal librations for 17-degree inclinations. What we learn is, well, that 60-degree inclination comes from the three-body problem, where you treat everything as point masses, and you more or less do orbit averaging. The two extra ingredients that help Pluto are this oblateness from the effective oblateness from the additional planets. So you go beyond the three-body problem, but also Pluto is in this orbital resonance with Neptune. So the resonance itself actually does some extra precession. Okay, so that balance, that competition between, and the resonance actually does some precession in the opposite direction from what in some ways, from what the oblate extra planets do, the oblate sun does. So competition between what the resonance is doing and what the extra planets are doing is what allows this oscillation to happen at 17 degrees.
Do they have comparable timescales, these two effects?
It must be, yes, they have to be, yeah. So we haven't figured out all the details of that yet. The resonance, how the resonance produces these precessions is actually very, very difficult to compute, because the resonance phase space is very, very complicated, and the precession rates can vary a lot across the resonance phase space.
If you want me to go first, there's someone on Zoom as well. Okay, I had a very small question and then a more broad one. The first one, I think if I recall your wording, you said that changes to Pluto's orbit are relatively robust. Is that right? To its stability, its robustness, or is it defined as changes to the mass and semi-major axis of the planets that you just mentioned on like your second last slide, up to like 20% and so on? Are those the sizes that you mean by relatively robust? Is like you can change things up to some like 20% amount?
No, the relative robustness I was talking about had to do with changes to Pluto's orbital parameters.
Okay.
Okay, so if you change Pluto's orbital parameters by a little bit within its own neighborhood, then you have that, we have the result that it's chaotic formally. The two Plutos will diverge exponentially, but they are not the orbit shapes and orientations still.
Okay,
So it's like local divergence and not a global
What about
divergence.
like a phase and not like a secular.
Yes, except, you know, it can't be a phase
Okay.
bounded because there is a constraint on the phase to maintain the resonances.
Okay, and my broad question, which you don't have to answer right now, we can talk later, is just about the orbital migration, like the migration of the gas giants and the hypothesis that Uranus and Neptune have switched places,
Mhm.
and how this fits in. It's sort of a broader question, but
Okay, we can talk about that.
I see a couple raised hands online, so let me just, I did not notice what order they came in. Sri?
Yes. Would this fortuitous orbital arrangement of Jupiter, Saturn, and Uranus play a role in the great inequality of Jupiter and Saturn?
Okay, good question. Certainly, if you move Jupiter and Saturn by some of that 10% effect, it would be problematic as far as the great inequality. I mean, it would change the great inequality greatly. So that wiggle room that I said for changing the masses and the same major axes of Jupiter and Saturn and Uranus, that would definitely affect the great inequality. You're right. Yeah. What is the great inequality? The great inequality is
Socially.
yeah, it's not a sociological term. It's so Jupiter and Saturn are very close to a 5:2 resonance, but they're not doing any kind of oscillation. But every time they have conjunctions. There's some extra perturbations because of this closeness, and there's a 900-year period where they alternate between going forward and going backward relative to the unperturbed state. Okay, so there's this 900-year period, and that great inequality has that 900-year period is associated with the difference between what the 2 to 5 resonance angle does. It actually circulates versus if it were actually in resonance and it was locked in resonance. Sufficiently complicated or confusing?
Thank
Norm?
you.
Oh,
Thank you.
Norm?
Yeah, hi, Renu. Thanks. That was great to hear that talk. Sorry I couldn't be there in person. You mentioned that the instability timescale is short when you're outside of this region that it's stable. And I wasn't clear whether you were referring to the Lyapunov time or a time for Pluto to be ejected. And of course, it makes a big difference. So what is the timescale for it to be, something catastrophic to happen as opposed to just the Lyapunov timescale?
Okay, so literally what we looked at in these simulations was how long it takes for it to drop out of this resonance. So the critical resonance angle doesn't lightweight anymore, so Pluto can have close encounters with Neptune on that timescale. So it's not a Lyapunov timescale, it's actually a timescale for large changes in Pluto's orbital parameters.
Okay, well, that's a very tight constraint then. Yeah, that's great, actually. So, you also had mentioned earlier about the late heavy bombardment being 500 million years, which is a lot longer than this instability timescale I got, right?
Right.
So my geophysicist or geochemical friends tell me that the evidence for the great late heavy bombardment from the lunar measurements has actually gone away because almost all the rocks that they used to date that, they were found in many different regions over the moon, but they were almost all from the same impact, which was very late. So there's no real evidence from the lunar record that there was a late heavy bombardment. That may not be true for the other features you were talking about. But the reason it's of interest, of course, is because 500 million years is a lot longer than the timescale you're indicating. And if you started outside of that stable region, and you could only be in it for tens of millions of years, then again, that doesn't sound like the migration lasted for that kind of long time scale. That's more of a comment than a question, I guess I'd say. The first part you already
Okay, I
answered.
was wondering what the question was.
Well, the question was what was the instability referring to? You meant a major instability.
Yeah, that's a major instability. Now, with regard to the lunar late heavy bombardment having the evidence for that having gone away, Norm, I have to put on a very critical thinking hat on that. I think the arguments that are being made that the evidence has gone away have to do with not being able to find a theoretical model to fit those. So we can't find.
No, I was just referring to geochemical evidence.
Oh, yeah,
right?
The evidence hasn't gone away.
No, that's what I'm saying. The claim is that the evidence has gone away. That is the claim from the geochemists.
So I think it's really an interpretation rather than the evidence going away. The interpretation is that all the lunar samples were collected from the near side of the moon. And so they were collected from the site of possibly a single major impact on the near side of the moon. But that's not quite true. And it's a long, it's a controversy. Let me put it that way. It's really interpretation. It's not that the evidence has gone away. It's that all of the samples came from one impact. That's the interpretation. The counter to that I've heard is that there are lunar meteorites that come from all over the moon, and they show the same signatures as the Apollo samples. There are also meteorites from Mars that show the same 3.94 billion year perturbation on the thermal history of crystallization of these meteorites. And so I'm not entirely convinced with the statement that that this is a true statement that the geochemical evidence has gone away. I think the interpretation has changed, and it's because the theorists can't find a good model to explain the evidence.
Well, the geochemists probably don't care what the dynamicists are saying, to be honest. So in that sense, I don't think that's the motivation. But I agree with you that the evidence from other planets is not affected by this argument.
Okay.
Hano, I saw a hand up, but
I have the same question as Norm about the late heavy bombardment.
I see. Okay. Well, do we have any final questions in the room? Otherwise, we can adjourn, and welcome to hang around. Okay, sure.
Well, so back to Brett's comments about this particular dynamics or particular fraction of stable orbits you're finding is applying to this particular set of parameters for Pluto. If you widen a little bit, it can get worse, can get better. In fact, it seems to, I'm getting the impression you're finding is that there's a new way to eject Pluto. Is that right? So instead of just letting it, the amplitudes of eccentricity gets higher and higher and encounter Neptune. It's actually a new dynamical path to
yes, it's a constraint on the latitudinal oscillation. It's a constraint from the latitudinal oscillation.
Right.
Yeah.
So there's a phase shrink.
Yes, it's possible for generally those 3 to 2 resonant orbits to be stable without having a latitudinal oscillation. Right. So there's some range over which they can be stable in those latitudinal oscillatory.
Even the high inclination, this is actually
well, at lower inclination that one might have anticipated. Yeah.
Right. So if we used to have 1,000 Pluto, we have to get rid of them. This is just adds a new way of getting rid of them, sort of.
Well, yes, I suppose.
We don't know how many other ways, but
yeah,
we need to get rid of them. Oh, it's a simple code.
Okay, any further questions? All right, let's thank Renu again.